Good morning, students. In the previous session, what we have discussed is electric field intensity due to various types of charges such as point charge, line charge and surface charge. We have seen the equation for all the three different cases. But now in this particular session, we are continuing with the same derivation, electric field due to a line charge. So along the line, the charges are uniformly distributed. So what is the objective of doing this derivation? See, in the previous session, we have derived the equation for elementary electric field at a point P due to elementary charge dq is given by dq by 4 pi epsilon naught into r square into a cap r. This is the equation for elementary electric field due to elementary charge dq along the line, okay, line charge distribution. But here we don't know the unit vector a cap r. So the objective of continuing this derivation is calculation of this unit vector a cap r in terms of trigonometric identities, okay. So this is the objective of this derivation. In order to do that derivation, we need to consider a line charge. We need to consider a line charge first, okay. So let us consider a line charge along the z axis. So let us name this as A and B. Let O be the origin of this line charge, okay. Now the distance between A to O is Z. The distance between origin and A is Z. So let us consider a point P at which electric field intensity to be determined. Let us consider a point P at which electric field intensity to be determined along the y-axis. Along the y-axis. The coordinate of this point is 0, y, 0. So which is placed at a distance r from the origin. Which is placed at a distance r from the origin. So the distance between the elementary length dz and the distance between the elementary length dz and point P is considered to be small r. The distance between infinitesimally small elementary distance dz and the point P is small r. The distance between dz and O is z. Okay, the charge at this point is dq. The charge at this point is dq. Got it? Charge at this point is dq. The angle formed at this point is theta. The angle formed at this point is theta. So let us resolve this vector. The unit vector is a cap r. Let us resolve this vector, so which gives the resultant like this, okay, it gives the resultant like this. So this angle is theta 2 and this angle is theta 1. Then this angle becomes what? If this angle is theta 2, what about this angle? This angle is pi minus theta 2 because this line gives the 180 degree. So 180 degree minus theta 2 is pi minus theta 2. This is the angle of this point, okay. So this is the geometrical representation to calculate the unit vector a cap r, okay. So the coordinate of this point is 0, 0, z. The coordinate of this point is 0, 0, z. Let us consider this as equation 1. Now the objective is to calculate this unit vector, right? So let us consider the elementary electric field due to the elementary charge dq is given by this equation. Now we need to calculate a cap r. What is a cap r? It is a unit vector which is defined as a cap r is equal to unit vector divided by its magnitude. We know that the magnitude of unit vector is r. In order to calculate this r, vector r, we need to calculate the distance between these 2 points by using distance formula, that is So x minus x, 0 minus 0 into a cap x plus y minus 0 into a cap y plus 0 minus z into a cap z. Why we have considered this one? So as I said in the previous sessions, it should be tip minus tail, tip minus tail. Okay. So by solving this, r is given by y into a cap y minus z into a cap z. Therefore, the unit vector a cap r becomes y into a cap y minus z into a cap z divided by r. Consider this as equation 2. Okay. See here, see the concept. This is the right angle. Consider the triangle, the point of elementary cross section is M. Let us consider the point of elementary cross section is M, because this is infinitesimally small distance. The distance is very, very small, therefore which will be considered as a point. So this point is considered as M. Therefore, which creates a triangle MOP, which creates a right angle triangle MOP. So according to this right angle triangle, we can able to find the distance Z, R and small r. We can able to find the distance Z, R and small r, which are essential to calculate the unit vector. Okay. Let us consider this triangle. Okay. This is 90 degree. This is M, this is O and this is P. What is this distance? R. This is Z. This is capital R. Let us write the trigonometric identities here. Okay. So trigonometric identity, this angle is theta. According to this, sin theta is equal to what? Sin theta is equal to opposite by hypotenuse, right? Opposite by hypotenuse, r divided by r. Cos theta is equal to adjacent by hypotenuse, z by r. Okay. Next, tan theta is equal to opposite by adjacent. So opposite is r, adjacent is z. Okay. Now we need to calculate the distances r, z and capital R. We know that capital R is equivalent to the y. Capital R is equivalent to y. No need to calculate this. So we need to calculate small r and z. So in order to calculate small r, we can resolve this equation as r is equal to capital R divided by sin theta. Therefore, this can be written as r into cosecant theta, because 1 by sin theta is cosecant theta. Okay. So small r is given by r cosecant theta. Similarly, we need to calculate the distance z. Distance z can be calculated as by using this equation. Z is equal to r divided by tan theta. We know that 1 by tan theta is cot theta, r cot theta. So by using this equation, we can easily find out z. So now we know the quantities, distance quantities r, capital R and z. We can able to substitute here, right? We can able to substitute at this point. So therefore, a cap r becomes, substitute these quantities in equation 2 and gives the unit vector a cap r, that is, what is this? Y is nothing but r a cap y minus z into a cap z divided by capital R. Capital small r is r cosecant theta. Okay. Okay. Continuing with this, we have got the equation for unit vector as y into a cap y minus z into a cap z divided by r. Substituting for unit vector in equation 1 gives rise to this new equation So now also we have got the equation for y, z and r. Y is nothing but capital R, z is nothing but r cot theta by using trigonometric identities what we have seen just now. Then small r is equal to r cosecant theta, right. So by substituting all these quantities into the above equation, we have got this equation. So what about rho L and dz? Why this dq is replaced by rho L and dz? We know that line charge density rho L is charge per unit length. So charge what we have considered at this point m is elementary charge dq at the elementary distance dz. Hence rho L is dq by dz. So in order to replace dq, we need to cross multiply this. Then dq is equal to rho L into dz. That's what we have substituted here. dq is equal to rho L into dz. And substituting all the quantities of y, z, r and dz into this equation, we have got this equation, right. See, what about dz? We know the equation for r is equal to r cot theta. So if we differentiate with respect to theta, then dz is equal to minus r cosecant square theta into d theta, because differentiation of cot theta is minus cosecant square theta. Substituting this equation here for dz, the resultant equation is given by this. See, we can cancel out this cosecant square gets cancelled, r gets cancelled, okay. We left with minus rho L d theta into r a cap y cot theta into a cap z divided by 4 pi epsilon naught into r square cosecant theta. By solving this equation further, we have got into this format, right. See here, you can look into this. So replacing cot theta by cos by sin, because tan theta is sin by cos, cot theta is inverse of tan. Replacing cot by cos theta by sin theta, we can get this equation, and solving this equation by taking LCM in the numerator and by taking 1 by cosecant theta as sin theta, we have got this equation, and solving further we will get into this form. This is the final equation for elementary electric field due to the elementary charge dq. In order to find out the total electric field at a point P due to the entire line charge AB, we need to integrate all the elementary electric field intensities within the given range. That given range is, the initial limit is pi minus theta 2 to theta 1. So we can see that in the geometric representation. See here, the angle at this point is pi minus theta 2 to theta 1. This is the initial limit and this is the final limit of integration we need to consider in order to calculate the field due to this entire line charge AB. Okay. So on integrating this, we will get the final equation for electric field intensity at point P due to the line charge. Okay. So let us continue with that. Okay. See, total electric field intensity E is given by integration from pi minus theta 2 to theta 1 dE. That is, E is equal to minus rho L divided by 4 pi epsilon naught into R. This is constant, take it outside. Then integration from pi minus theta 2 to theta 1 into sin theta into a cap y minus cos theta into a cap z into d theta. Integrating with respect to theta gives minus rho L divided by 4 pi epsilon naught into R. On integrating this, see, what is the integration of sin theta? Cos theta minus cos theta with the integration limits pi minus theta 2 to pi into a cap y minus, what is the integration of cos theta? Sin theta. Sin theta with the integration limits pi minus theta 2 to theta 1. theta 1 into a cap z. Okay, this is the integration limits. On solving this, total electric field intensity is given by minus rho L divided by 4 pi epsilon naught into r, see, minus of cos theta 1 minus cos of pi minus theta 2, okay, into a cap y minus sin theta 1 minus sin of pi minus theta 2 into a cap z. This is the equation. So, on solving this, so E is given by minus rho L divided by 4 pi epsilon naught into r. Solve that equation. Take minus here, cos theta 1. So, what about cos of pi minus theta 2? Cos of pi minus theta 2 is minus cos theta 2. According to trigonometric relationship, cos of pi minus theta 2 is minus cos theta 2. Similarly, sin of pi minus theta 2 is sin theta 2. So, on substituting these things into that equation, the resultant equation is cos theta 1 plus cos theta 2 into a cap y minus continuing with that sin theta 1 minus, this can be replaced by sin theta 2 into a cap z. This is the entire equation. So, take negative sign common, then these two will get cancelled. Therefore, total electric field intensity E is given by rho L divided by 4 pi epsilon naught into r into cos theta 1 plus cos theta 2 into a cap y minus sin theta 1 minus sin theta 2 into a cap z. This is the total final equation for total electric field intensity due to the line charge, okay, at point P along the coordinates 0, y, 0, influenced by the coordinates 0, 0, z. So, on solving this equation further, we can represent this equation in terms of coordinates also. Okay, this is the final equation you need to refer for solving few problems. Okay, in continuing with this, so this total electric field intensity equation can be replaced by using the coordinates. By using the geometrical coordinates, we can solve this equation further by taking some geometric considerations and trigonometric considerations. Consider the same geometrical shape, see, but the difference is the distance between O and A is now considered as Z1, distance between O and B is considered as minus Z2, because this is a negative Z axis, hence this distance is minus Z2. The coordinate at point B is 0, 0, minus Z, coordinate at point A is 0, 0, z. Since it is a positive z axis, this quantity is positive and this quantity is negative because it is a negative z axis. This coordinate remains same at point P, at which we need to calculate the total electric field intensity. By considering the Pythagoras theorem for AOP triangle and BOP right angle triangle, we can get the hypotenuse distance AP as square root of r square plus z1 square, and the hypotenuse for this triangle BOP, so then hypotenuse is BP, which is given by square root of r square plus z square, because minus of z2 whole square is positive. So that's why I have written directly. Then BP is equal to this one and AP is equal to square root of r square plus z1 square. Okay. Then we need to have the different quantities cos theta 1, cos theta 2, sin theta 1 and sin theta 2. We need to substitute for these quantities. So how to calculate these quantities by using these two right angle triangles? See, we have the sin theta 1 is equal to opposite by hypotenuse. Sin theta 1 is equal to opposite by hypotenuse. What about hypotenuse? Hypotenuse AP is given by square root of r square plus z1 square. Similarly, sin theta 2 is equal to r divided by BP. So what is BP? Square root of r square plus z2 square. Similarly, cos theta 1 is adjacent by hypotenuse. So cos theta 1 is adjacent by hypotenuse, that is z1 divided by hypotenuse AP is square root of r square plus z1 square. Similarly, cos theta 2 is adjacent by hypotenuse, that is minus z2 divided by BP, that is square root of r square plus z2 square. Substituting all these four quantities into the above equation, then the resultant is E is equal to rho L divided by 4 pi epsilon naught into r into, what is cos theta 1? Cos theta 1 is z1 divided by square root of r square plus z1 square. Okay, plus cos theta 2 is minus z2. I can write like this, minus z2 divided by square root of r square plus z2 square. Okay, into a cap y, plus this plus comes here into sin theta 1. What is sin theta 1? R divided by square root of r square plus z1 square. Okay, then minus sign comes here, sin theta 2. What is sin theta 2? R divided by square root of r square plus z2 square into a cap z. This is the final equation. So this is the equation for electric field intensity at point P in terms of coordinates, in terms of geometrical coordinates. Okay, we can resolve this unit vector in terms of geometrical coordinates as well as in terms of trigonometric considerations. Okay, so we can represent in both the ways. So there is a special case when this length of this charged wire AB is infinite. What happens to this equation? The consideration is when the length of the charged wire is infinity, then what happens to these two equations? See here, the special case we can consider here. Special case, when the length of charged wire is infinity, when the length of charged wire is infinity, when this goes to infinity, that is plus infinity, and this comes to minus infinity, that is where we can say the length of this charged wire AB is infinity, right? So the positive extent is plus infinity, the negative extent is minus infinity. When this happens, so when point B goes to minus infinity, then theta 2 becomes 0. When point A goes to plus infinity, then theta 1 becomes 0, right? When point A goes to plus infinity, theta 1 becomes 0. And when point B goes to minus infinity, theta 2 becomes 0, right? Substituting theta 1 and theta 2 0 into the above equation, what you will get? Okay, see here, I will write here, substituting theta 1 and theta 2 0 in the equation, then E becomes rho L divided by 4 pi epsilon naught into R into cos 0 plus cos 0 into a cap y plus sin 0 minus sine 0 into a cap z. What is cos 0? 1. What is sine 0? 0. Then E is equal to rho L divided by 4 pi epsilon naught into R into 2 a cap y. Cos 0 is 1, 1 plus 1, 2, 2 a cap y. This quantity becomes 0, entirely 0. Then the final equation E is 2 into rho L into a cap y divided by 4 pi epsilon naught into R. Similarly, rho L to a cap y divided by 2 pi epsilon naught into R. This is the equation for the electric field intensity at point P due to the infinite length charge. When the length of the line becomes infinity, then the equation gets reduced to this format. Understood? Okay.